Hi there, welcome to this video. My name's John. I provide mathematics tuition for A-level maths, A-level further maths, 6-term examination papers and mathematics admissions test. Warm welcome to this video where we're going to take a look at finding the nth roots of a complex number. So this is clearly more targeted towards further maths students, A-level further maths students who are more likely to come across complex numbers. Though, if you are doing normal maths and you've gone maybe a bit beyond the specification, maybe you've had a look at some of the further maths stuff, even though you might not be sitting the exams, then this might be an interesting video for you to watch as well. So finding the nth roots of a complex number is not a particularly difficult thing. I think a lot of people have trouble with this because they don't necessarily understand some of the steps that they're taking. This is a very common thing with mathematics. I think that if you're just given a method for doing something and you don't really understand that method, it can be very difficult for you to apply it properly. And I think that's the case with finding the nth roots of complex numbers. So I'm going to try to explain as much as I can throughout this video what I'm doing, why I'm doing it, and so on and so forth, so that you have a chance of understanding. This is just my way of going about things. I'm not saying that my way is unique necessarily in any way. I'm not saying that my way is the way of going about things or the best way or the only way. It's just my way. It's just the way that I go about finding the nth roots of a complex number. Something that I know that I can do that's fairly systematic, fairly routine. And unless I've got a specific reason for doing so, then I typically won't change my approach to finding the nth roots of a complex number. Not that I need to do it that often anyway. It's just not something that you do that often. Okay, so let's say we've got a complex number, x plus iy. What do we mean by the nth roots of a complex number? Well, we're looking to solve the equation z equals the nth root of x plus iy. We're trying to find those complex numbers z such that when we raise z to the power of n, we get x plus iy. Okay, so rather than thinking about things as z equals the nth root of x plus iy, it's better for us to think in terms of z to the power of n equals x plus iy. Typically, there's going to be, for a non-zero complex number, so we're going to assume here that x plus iy is non-zero, otherwise, because it just means that we're going to have to possibly create special cases and consider special cases and things like that, which I don't really want to have to do. So we're talking about non-zero complex numbers here. So x plus iy throughout the duration of this video is going to be a non-zero complex number. Generally speaking, for a non-zero complex number, then there's going to be nth roots for that complex number. Okay, nth roots. It might seem obvious. It's not necessarily an obvious thing, but there will be n distinct nth roots for that complex number. And we want to find all of them. So when we want to find the nth roots of a complex number, what we're talking about is all of them. Okay, so not just one of them, not just a couple of them, it's all of them that we're looking for. Now, in the form that we have here, so this, I guess, kind of Cartesian form, x plus iy, things can be a little bit difficult. Okay, it's going to be much easier for us to deal with this kind of problem, finding the nth roots of a complex number, if we consider our complex numbers in either exponential form or trigonometric form. Okay, so we might have, for example, if we take the x plus iy, then we can think about this either in the form e to the power of re to the I theta, or r times cos theta plus I sine theta, where r is equal to the positive square root of x squared plus y squared. In other words, the modulus of x plus iy. Okay. Now, I personally prefer, in this particular context, the trigonometric forms. That's just my personal preference. There's no reason why what I do during this video there's no reason why you can't use exponential forms. And I'm also not suggesting that I've got anything against exponential forms. I will use them whenever I feel that it's convenient for me to do so. Okay, but in this particular context, I prefer to use the trigonometric forms. Okay, so let's write our equation. I'll just scroll a bit too far down there. Z to the power of n equals x plus iy. Let's have a look then. So if we've got z equals modulus of z, let's formulate this in a trigonometric form. Modulus z equals the modulus of z cos phi plus I sine phi. Okay. So what we need then is what we're interested in is z to the power of n. Z to the power of n, which of course is going to be equal to the modulus of z to the power of n times cos phi plus I sine phi to the power of n. Now, those of you that are familiar with De Moivre's theorem, so here n is a positive integer. Maybe I should have said that earlier, but if there's any doubt about what the value of n is, it's a positive integer. It represents a positive integer here. So we can use De Moivre's theorem, no problems. And we get cos n phi plus I sine n phi. So we're trying to solve the equation, find the solutions to the equation. Modulus of z to the power of n cos n phi plus I sine n phi is equal to r cos theta plus I sine theta. Now there's a bit of a problem here. Because theta and phi, we need to restrict them in some way. Okay? Because if we don't restrict them, what can happen is we get multiple representations potentially for each complex number. Right? So, for example, if we take the complex number I, if we're not careful, we can write this in trigonometric form as, let me get this right, it's going to be cos pi by 2 plus I sine pi by 2. Or we could write it as cos 5 pi by 2 plus I sine 5 pi by 2. Or we could write it as cos minus 3 pi by 2 plus I sine minus 3 pi by 2, and so on. Okay. This is going to play a big role. I'm going to touch on this towards the end of the video. I think I'm going to say something a little bit more about this. So what we want to do really is we want to restrict things so that we've got unique representations for our complex numbers. So we're going to restrict the range of values of theta and the range of values of phi. Okay, so let me just get rid of this. We're going to restrict to a 2 pi range. Okay, remember sine and cos are periodic functions. They've each got a period of 2 pi radians. We're going to tend to work in radians, by the way. They've each got a period of 2 pi, so they repeat themselves exactly every 2 pi radians. Okay, so we need to restrict theta and phi to suitable 2 pi ranges. What's suitable? Well, it depends to a certain extent on the context. Okay, so For example, we might restrict phi to minus pi, less than phi, less than or equal to pi. Okay, and it's got to be a non-overlapping, so to speak, 2 pi range. So we would not include, and what I mean by non-overlapping is that if I included the minus pi here, if I had the range minus pi is less than or equal to phi is less than or equal to pi, if you think about the Argand diagram, there's going to be an overlap here where all of the numbers on the negative real axis, they're all going to have two representations, potentially two different representations. That's what I mean by overlapping. So we want to avoid that. So this would be one suitable 2 pi range. I mean, it depends on the context, but we can also choose, for example, and there's another common one, which is 0 is less than or equal to phi, which is less than 2 pi. Again, it's non-overlapping. But basically, any 2 pi range, in theory, will suffice. It's just, these are the two most common ones, and for the purposes of this video, I'm going to choose this latter. So 0 is less than or equal to phi, and the same for theta as well, which is less than 2 pi. Okay. So let me get rid of the that other one. But sometimes you will see other ranges, and you have to just be prepared to adapt to whatever situation you're presented with. And you've got to pay close attention to what are the ranges that are involved for theta and phi and so on and so forth. If there isn't a range given, you need to decide on a suitable one yourself. But like I said, you might be presented with sometimes different 2 pi ranges. It's very unusual to have one that's different from the two that I've just given. But if you are given one that's different from those, then you've just got to roll with the punches, and you've got to deal with it. You have to understand what you're doing well enough to be able to take that into consideration. Okay, so we're also going to have the same range for theta. We don't have to, by the way. We don't have to have theta and phi having the same ranges. It's just why make things more difficult than they need to be? Okay. Now, z to the power of n, if you notice, involves n phi. Okay, so I've just highlighted it on the screen. N phi. And I think this is where a lot of people get confused. Because the range of n phi is not 0 less than or equal to phi is less than 2 pi. The range of n phi is 0 less than or equal to n phi is less than 2n pi. Okay, so this series of inequalities, 0 less than or equal to phi less than 2 pi, multiply through by n, and you get this 0 is less than or equal to n phi is less than 2n pi. So that means that n phi has a greater range. It's n times greater than phi. Okay, and again, this is where people kind of get confused, which is unfortunate. Okay, so let's bear that in mind. It might be worth you taking notes, by the way, for this video, because I can't necessarily keep everything on the screen. If I do need to refer back to something, I might scroll back up, but sometimes I won't. Okay, so let's have a look then. So going back to our equation, let me just get rid of these red circles. Okay, so we can take this in two steps, or two parts really. So on the one hand, we've got modulus of z to the power of n is equal to r. So we're dealing here with positive real numbers and really non-zero, because the only time that the modulus of a complex number is going to be 0 is if that complex number is 0. So these are r and modulus of z and modulus of z to the power of n are all positive real numbers. And we know how to find nth roots of positive real numbers. And if we need to, it's the positive nth root. Right? So for example, if we had modulus of z squared equals r, then the modulus of z would be equal to the positive square root of r. Because modulus of z is a positive real number. So there's no point in taking the negative square root of r. So it doesn't make any sense. So we're talking about positive nth roots wherever appropriate. And what we can say, and we know how to deal with extracting nth roots of positive real numbers, at least on a theoretical level, and that's all we need to know. Then what we get is that the modulus of z is equal to the nth root, positive nth root of r. Okay, that's easy. Okay, we're done with that. So then we come to equating effectively cos n phi plus I sine n phi with cos theta plus I sine theta. Well, there's an obvious solution to this. The first obvious solution is n phi equals theta. Okay? N phi equals theta. But remember, that theta is in the range 0 to 2 pi. Including 0, not including 2 pi. But n theta has this greater range. It ranges from 0 to 2n pi. Okay? So that means that n phi could also possibly be equal to theta plus 2 pi. But it could also be equal to n phi. N phi could also be equal to theta plus 4 pi. So all I'm doing here is using the periodicity of sine and cos and just keep adding 2 pi onto this. Okay, so I've got how could I think about it? I could think about it maybe in this way. I've got 0 here, and I've got 2n pi up here somewhere. And so I can split this up into 2 pi ranges. 2 pi, so this is like a real number line, for example. 4 pi, 6 pi, and so on and so on and so on. Okay, so then right up here I'm going to have, I'll write it up here just to give me a bit more space. 2n minus 1 pi. Okay, so theta is, and this is the range of possible values for n phi. N phi can be anywhere from 0 to 2n pi, including 0, not including 2n pi. So theta is going to be somewhere in this initial 2 pi range. Okay, this is where theta is going to be. So if I add 2 theta to this, then I end up in the next 2 pi range. Okay, so plus 2 pi. And then add 2 pi again. I end up in the next 2 pi range. So I just keep doing this. I just keep adding 2 pi and bouncing along until I end up in this final region here, in between 2n minus 1 pi and 2n pi. Okay. So how many times can I add 2 pi to theta? Well, n minus 1 times, right? So I can continue this. Let me just get a bit more space here. So n phi can go right up to theta plus 2n minus 1 pi. Okay, so these are the possible values for n phi, and therefore the possible values of phi are going to be phi equals theta over n, theta plus 2 pi over n, all the way up to theta plus 2n minus 1 pi over n, which I could write more succinctly as the following. So I could say phi is equal to theta plus 2k pi over n. For k, an integer, k is equal to 0, 1, 2, up to n minus 1. So notice that there are n values of k here. each value of k corresponds to, effectively, one of the nth roots. So then I can write out my nth roots if I want to. When I write out my nth roots, I can stick with the trigonometric form, or I can use the exponential form if I want to. So what are the nth roots of this? Actually, it might be better for me to use the exponential form in this case. So we get z is equal to what was it? The nth root of r e to the I theta plus 2k pi over n for, again, k is an integer, k equals 0, 1, 2, up to n minus 1. Okay, that's it. They're my nth roots for this complex number. And that's, generally speaking, how I personally would go about finding the nth roots of a complex number. And I'm not unique in this respect, by the way. This is a very common approach for doing things. It's just I find it very reliable and very systematic and very useful. Okay, so unless I've got a reason for doing otherwise, then I will stick with this. And there might be occasions from time to time where I feel that I need to slightly change my approach. Depends on the circumstances. Okay, so there are other reasons why we need to restrict the values of theta and phi and things like that. So one of the problems is if we don't have unique ways, a unique way of expressing each complex number, the following kind of situation might happen. So let's take the number, let's take I again, okay? So we've already seen I can be written as e to the power of I pi by 2. We write it in exponential form. Or it could be written as e to the 5. I'll write it as I times 5 pi by 2. Or e to the I, not 7, 9, sorry. 9 pi by 2. So all I'm doing is just adding 2 pi on each stage. Okay. And I can go in the other direction as well. So now, let's check this out. So we've got I, clearly I equals I. So I'm not saying that this is correct reasoning, by the way, what I'm about to do here, but just to show you why we've got to be really careful sometimes. So there is something wrong with what I'm about to do, but I'm not going to get into too much detail with it. It's really just to highlight that there is a problem. There is an issue if we're not careful about things. So if we just assume that the normal laws of indices apply to complex numbers without any modification, we can get something like the following happening. Okay, so since I is equal to I, that means that e to the power of I pi by 2 is equal to e to the I 5 pi by 2. Now this is not, there's nothing unusual about this, by the way. So cos pi by 2, for example, is equal to cos 5 pi by 2. So there's nothing strange with a function having the same value for two different arguments. There's nothing weird about that. So if we use the usual laws of indices naively, and I'm not saying that the laws of indices that we use for real numbers do carry straight over to complex numbers, but let's just hypothetically see what happens if we assume that. Then what happens? We get e to the I pi by 2 to the power of I is equal to e to the I 5 pi by 2 to the power of I. Scroll down, give myself a bit more space. So I get e to the I times pi by 2, I pi by 2 times I is going to be minus pi by 2, which is a real number. And this evidently is equal to e to the, well, I times 5 pi by 2 times I, again using laws of indices, so we're using this law of indices, a to the power of x to the power of y is equal to a to the power of xy. Then I get minus 5 pi by 2, which again is a real number. But hang on a second, e to the minus pi by 2 is a different real number to e to the minus 5 pi by 2. So what's gone on here? Why have I got equality? And the answer to this is because the laws of indices, as they apply to real numbers, don't automatically just carry over unchanged to complex numbers. There is a problem. There are serious problems when it comes to raising complex numbers to complex powers, imaginary powers or complex powers. There's some serious difficulties involved with this. When it comes to complex numbers to real powers, this is no big deal, okay? But complex numbers to complex powers or imaginary powers, much more difficult, okay? And if we're not careful, things like this can happen. So what you'll probably see is, if you look in Google or something like that, ask your teacher, whatever, what's the value of I to the power of I? You'll almost certainly get the response e to the power of minus pi by 2. And this is only partly true, though, because I to the power of I, which is what we're effectively calculating here, could also be equal to e to the minus 5 pi by 2, e to the minus 9 pi by 2, e to the minus 13 pi by 2, and going in the other direction, you get e to the 3 pi by 2, e to the 7 pi by 2. So there's an infinite number of possible values. And this is if we allow non-unique representations of our complex numbers by allowing effectively our arguments, the arguments of our complex numbers, to range without any kind of restriction. Okay. It's only when we apply suitable restrictions that we can kind of fix this problem. Okay, so I'm not going to say anything more about that. That's something that you'll do if you go to university and you get into complex analysis and things like that. Then you'll deal with things like this. But it is just highlighting a problem, an issue with complex numbers and dealing with exponents, particularly complex exponents of complex numbers. Well, actually, complex exponents of even if I'd chosen 1, for example, here, I would have been able to derive a similar result. Okay, 1 to the power of I is not necessarily equal to 1 if we don't choose the right kind of range. Okay, so that brings us to an end, to the end of this video. So hopefully you found something useful in this video. If you do have any questions about anything, please ask any questions that you have in the comments section. I don't make any money from making these videos, but it would be really nice if you could show your support for these videos by hitting the subscribe button and hitting the like button. I do want to continue making these videos because I do want to help people, but I can only justify making these videos because they take a lot of time. I can only justify making these videos whenever I've got the support for doing so. So if you do appreciate these videos and you want me to continue making them, then please let me, please show your support. Also, if you think that there is anything that I could be doing differently in the videos, please let me know. Because currently I'm kind of making the videos just for me, in a sense. For me as I was when I was an A-level student. What I think I would have found interesting and useful back when I was an A-level student. But that's me. I want to be helping other people, really, current A-level students. So if you are a current A-level student, how can I help you? How can I better help you with my videos? Let me know, okay? Constructive criticism, constructive feedback is always welcome. Non-constructive criticism, non-constructive feedback, not so much. So I'm going to leave it there. Thank you for watching, if you've made it this far, and I hope I will see you in the next video. Thank you.